1. The lecture hour is Monday 2 to 4, suppose, or 2 to 3:30 something. And tomorrow, then Tuesday, 2 to 4 as well, 2 to 3 something. All right? So there are 3 lecture groups. So make sure that you come to the right lecture group. All right? Of course, you can go to other lecture groups, and other lecture groups members can come to this one, but officially, I think that's the list. So I think I have 250 students in this group. All right? So no need to hurry, just chit-chat only. All right? I was told that. Okay. About the first thing is about the lecture notes. So different groups may have slightly different lecture notes. All right. So if you come to this lecture group 1, so you better download the lecture notes for group 1. For group 1. It's a bit confusing at this moment. So check my name. All right. What's my name? You know my name? You don't aware? You did not aware there's 3 lecture groups. So just download the one that you access. Maybe you got the wrong lecture notes. Okay. My name, my last name start with C. The other, there's one more lecture also start with C. Okay, my name is Chan Yu Man. All right. So it's group 1. We try to identify as group 1, but somewhere there may be problem. But lecturer's name should be there. All right. So get group 1, and we are in a transition. We have IVLE, which is going to phase out. No more IVLE next academic year. And we have this new member, Luminous. Have you used Luminous before? Last semester? Today, terrible. You even can't log in. Right? Is that what you get? All right. I have the same experience today. Okay, so at the beginning, I tried to upload the lecture notes, IVLE as Luminous. So at least for chapter 1, for group 1, the lecture notes are available in IVLE as well as the Luminous. Check for me, if not, let me know. But later on, I may just concentrate on one. So if we decide to use Luminous throughout the semester, then you can only download the notes in Luminous. There are 3 groups, right? So how about tests, mid-exam, tutorials, all this? There are only 1 midterm test for every group. Okay? 1 exam for every group. Wow. So here, now I learned a new things that we're going to discuss called union. So I read lecture notes from group 1, lecture notes from group 2, lecture notes from group 3, see the union. Wow. Then I won't miss anything. So to prepare for my exam and prepare for my midterm test. Okay, they are slightly different, but basically they will cover the same topics. So there are not much difference. So don't worry about it. Oh, if I cannot access to the lecture notes of other groups, what happened? Don't need to worry. All right? Okay, so midterm test, exam are all set for all 3 lecture groups. 1 test time, 1 exam time. Tutorial questions also. 1 set of tutorial questions for all 3 lecture groups. So basically, there's no difference in terms of continuous assessment. All right? I understand there will be a number of tutorial groups. Yeah, okay. let me pause for a while. All right, I'll continue. By the way, there may be a good news or bad news for you. I plan to have webcasts for this module. Yes. And it's also very bad. So you don't come for some of you. It's not a good choice not coming for lectures. You give up your chance of interact with the lecturer. You have questions, you don't come, I don't know. All right? You can ask me during the lecture, during the break, or after the break, so after the lecture, so that I am aware of what type of problems that you may encounter. So, by the way, I say webcast, but I did not mention when I opened the webcast. I may opened it the day before the midterm exam. Oh, doom. Maybe you get used to open it just after the lecture, but I may hold it for a while, right? Make sure that I can attract enough of you to come here. All right? I strongly advise or suggest you to come for the lecture if you can. All right? I see your face. Maybe you don't ask questions, but I see your face that you may have problems with what we discussed. All right? Especially those in the first few rows. I can see your face clearly. Those at the back, I cannot read their face. All right? Okay? Okay, the webcast may be stopped already. But they usually cut out the first few minutes. Settle. Have 250 students. I hope there's still time for others to come. Oh, move to the front. Thank you. Can't hear. Those at the back, can you hear? No. Yes. Confusing. Oh, no. Okay. So how about now? Can you hear? No. Then you better move to the front. Okay, how about now? Those at the back can hear? All right, thank you. Okay, let's start again, right? Welcome to ST2334, Group 1 lecture. All right, the lecture time is Monday 2 to 4 and Tuesday 2 to 4. All right. There are three lecture groups, and they are more or less the same except the timing. All right. So if you are assigned or you register for this group, so you come for this group. As for the lecture notes, for the time being, I upload the lecture notes in IVLE as well as Luminous. All right, but I believe that there may be some hiccup problems for Luminous, or it's so popular that you may have problems accessing Luminous for the time being, for today. Okay, so you can download it from IVLE or Luminous. But once we start, all the groups, instructors decide on the platform to use. We'll just use one platform. Most likely will be Luminous. All right? So from that onward, the lecture notes will be uploaded to Luminous only. But for the time being, I upload it through IVLE as well as Luminous. Group 1, under Group 1. All right? Although there are 3 lecture groups, but the tutorials, the self-tutorials, the midterm tests, and the exams, all right, will be the same. There's only one set of tutorial questions, one midterm test, and one final exam. So far, any questions? Yes. As you're watching, there's supposed to be webcast. All right. but I suggest you come to the lecture so that we have interactions. At least you have chance to ask questions, and I have chance to understand what the problems are. I need feedback. All right, so please, if you can, come to the lecture. Ask questions, answer questions. All right. Okay, so that's about all, right? Do I miss anything? You have any questions? No questions, ah? Is it a tough course? Yes. Every time, every module we have the same questions. Is it a tough course? Depends on what's your expectation. All right. Okay. To some of you, the module may be a little bit mathematical. All right. But in fact, it is the mathematics is very minimal. All right. There will be some counting problems. All right. That to some of you may be very hard, but especially for those from School of Computing or even engineering, counting is very important. Counting is not just count 1, 2, 3, 4. It's really important when you write your program, consider a problem, how to solve a problem. You must know all the possible combinations and way to do things. All right. Probability. Yeah. So whether this is a hard course, so I would say it's not a hard course. All right. But if you have problems in the mathematics part, then you have to do a little bit more revisions. All right. How many of you here are from School of Computing? Please raise a hand so let me have some idea. Not many. Which program are you from? Which program are you from? Computer engineering. So it's a joint program between. Yeah. What's wrong? Right? Between the engineering faculties and School of Computing. Any students are from Faculty of Arts and Social Sciences? Few. 1, 2. All right. Yeah. Design and Environment. School of Design and Environment? No? Okay. Then how about Faculty of Engineering? Okay, thank you. So, anyone from the science faculty? Okay. So, majority are from School of Computing and some from engineering. Okay. Okay. So, let's see. Let me okay. This is just to give you a brief idea of what the modules is about, what are the topics that we are going to cover, and it's still blank out. I didn't aware that one switch for mute and one button for mute and one button for unmute. It's not on-off thing, so when I press it, it's still mute to mute. Okay, so now I will upload it. Don't have to take pictures. All right. Here's my name, Chan Yu Man. All right. So these are the two references. We don't use textbook, but these are the two references. In fact, any books called Probability and Statistics may be useful, or Introduction to Statistics, all right, can be used as a reference. All right, and but these two are the one that we suggest. So these are the topics that we will cover. So the first part is on probability, basic concept of probability, which, all right, so this is a hard part, all right, and then we work on probabilities, and this is also hard. Conditional probability. Okay, but I say hard, but in fact, laughing is not that hard. All right. Okay. Then we will discuss about random variables. And random variables. You know what is variable? You know what is a variable? You know what is a constant? Constant is always the same, right? So the opposite is that variable. Variable means that it can change the values. Then what is random variables? Random variable is a variable that has a probability or a certain uncertainty associated with the values. So for example, x can be take 0 or 1, two values. So that is a variable, all right? Because it can take 0 or can take 1. So now, if it takes the value 0 all the time and takes the value 1, 0 of the time, then it's not a variable. It's always 0. All right? So random variable means that the variable will take certain value with certain probability. It's not 0, 1. Okay, we take certain, for example, it takes the value 0 with probability 40%, while it takes the value 1 with 60% chance. We don't know the value, but we know that it would take the value 0 with probability 0.4, while take 1 with probability 0.6. So that is a random variable. It's a variable, and associated with each values, there's a certain measure of the uncertainty. Sometimes it's probability. So it's random variable. So for random variable, we try to describe or understand it. So we consider something called distribution, and we talk about expectation of the distribution and things like that. So that is the second part. The third part is more practical. It's some common distribution, probability distribution. So the most well-known one, simple one, is tossing a coin. So there are two outcomes, right? Tossing a coin, there are two outcomes, right? What are these two outcomes? Head and tails, right? So we map head to 0 and head equal to 1. Or let's call it, I define a variable is the number of heads when I toss the coin one time. Toss the coin one time, if I got a head, then this variable takes the value 1. If it got a tail, this variable got 0. 0 heads. All right? So 0, 1. So if it's a fair coin, then it will be 0.5 for each of them, for each of the outcome. All right? So, so that is the simplest distribution that we can have, called Balloonian distribution. And then Balloonian distribution. Oh, you saw it's binomial. Yeah, yes. Binomial is a more general case. All right? Balloonian is for only one, toss one time. All right? We'll cover that. All right, after that, yeah, our friends this must be very familiar for those who've gone through A-level mathematics, gone through poly mathematics. You must know this normal distribution. All right. So we'll, revisit our old friend, normal distribution again. Why? Because it's very, very useful, very important distribution. All right. And then we move on to talk about statistics. Do you know what is statistics? Don't bother what is statistics, right? But you must know that what we're trying to do in statistics, all right, at least part of it, is to try to draw inference about the population based on a subset of the population, which we call a sample. That means we try to base on a small part of the population, which has to be taken appropriately, and then try to draw inference about certain characteristic of the population. So we need to know how does the sample quantity behaves, which we call sampling distribution of certain thing, and then we try to draw inference based on two types. Test certain statement, whether it's correct or not. Test whether we accept certain statement or not. All right, that is called hypothesis testing. The other one is to estimate certain characteristic of the population. The most common one is the mean. All right, the population mean. I want to know what's the population mean. I take a sample. I calculate the sample mean. So it's likely that we use the sample mean to estimate the population mean. Now, I think to some of you, some of you may not able to distinguish between a sample mean and a population mean. What is a population mean? Population mean is the mean of the whole population. There's only one number. You are talking about the same population, there will only be one number, one population mean. All right? Then sample mean is not fixed because it depends on your sample. I take a sample, I take a subset only and calculate the average. I take another subset, I calculate another average. They cannot be the same. A simple example is like this. Suppose, for those who attend today's lecture as considered as the population, all right? Everyone here. Not those who are watching the webcast now. Those who are here, consider as the population. So if I want to know that maybe average, your CAP is too much. Let's consider a simple one, height. All right? Everyone has a height, right? You don't want to I don't think you don't want to tell us what is your height, right? All right, but you don't want to tell us what is a CAP. Okay, let's consider we're interested in the height. So I want to know what is the average height of this population. So there's only one answer. I measure everyone and take the average. So that is one number, population mean. While the sample mean means that I take a sample. Let's say I take a sample of 20. Oh, I select 20. All right? I take the first 20 here. All right? And then measure the height. So I got one number. I can also take the 20 in the last two rows and measure the height. Are these two numbers the same? What do you think? Are they the same? Definitely not. Okay. In probability, it's almost not the same, right? By chance, it may be the same, all right? But it's very, very, very small chance, all right? Okay, so in other words, the sample mean depends on different samples. So different sample give us a different sample mean, all right? We don't know which sample we got. Hey, suppose I have, let's say 200. Choose 20 out of 200. How many ways can I form a sample of 20 from 200? We will learn it, all right? Based on combinatorics, all right? So what I mean is that the sample mean is sort of vary, so we call it a random variable, all right? Unless you really take the sample, really measure everyone in the sample, we call that a realization of the sample mean. So, generally speaking, we just call the average of a sample, which we only identify as x1, x2 up to x20. They are random variables. All right? So we calculate the average of them. But when you really take the sample, then you measure everyone and you will get the realization. You got a number for that sample mean, but for that sample only. So you have to see the difference between the population mean and the sample mean. Population mean is a constant. Oh, by the way, I say population mean is a constant. Do we know this constant? Yes, we know. No, we don't know. The third answer is, I don't know. Hey, the difference is, yes, I'm pretty sure that we know. What is it? No, we don't know because there's no way that you know. All right? The third answer is, I really don't know. Okay, so do we know the population mean? I say it's a constant, right? Okay, let's put it this way. Unless you measure everyone and take the average, then you know. So in other words, the answer is there. But you have to distinguish. Constant does not mean that you have to know. Sometimes you don't know. All right? So the problem in statistics is that there's a constant, but we don't know where it is. What value is it? So we try to, based on the sample, to look for the value of this population mean. All right? So remember, let's summarize it. Populations characteristics are constants, but may not be known to us. If I know the population mean, why bother to take sample? Right? You don't need to take sample. Why we have to take sample? We want to get some idea about the population. Population mean. So that's why I take a sample. So let me ask you, if I want to know the variations about the height of this group, so how am I going to do? Let me repeat the question again. I'm talking about the height, so I know the average. I want to know the average height, so that's population mean. Now I also want to know the variation among the height of all these groups, these people. So that's the variance and the population variance. Is that constant? Of course it's a constant. Do we know that constant? We don't know. Unless you measure it, everyone. 200 may be okay. Think of it, 2 million. Can you measure 2 million? Yeah. I can't. All right, so how to estimate it? Again, I take a sample, look at the sample, measure the height. Then I calculate the sample variance of this group. And then estimate the population mean. All right? So that's what we are going to do in later part of this module. Okay? Yeah. So now we start. The real, by the way, I forgot the most important thing. I hope this information is correct at this point of time now. Yeah, what you worry, what you interested most. CA, okay, there only one CA, one midterm test, 30%. Okay, this is tentative. That's what I remember about. I need to verify, confirm with the other lecturers. But there's 30% for the midterm test. It's likely in the week 7. Week 7, 1 week after the semester break. All right. It's likely to be in the maybe in the evening or in the weekend. All right, because there are 3 groups, 3 lecture groups. So we have to arrange a time that is available or suitable for most of us. All right, final exam 70%. At this point of time, it's like, okay, the chance of open book of all this, midterm test or final exam, is almost zero. Yeah. I have to talk in probability, right? So, open book chance zero. Almost zero lah, okay? Almost zero. That means basically zero. So it's closed book. The only variation is whether there will be a cheat sheet allowed or not. All right? We'll let you know later. All right? Good news, no open book. You know how difficult our open book exam is. Yeah. All right? Okay, so what? Finish lah. I still have more than 1 hour time. Okay. Okay. Let's start the real business. Chapter 1, basic concept of probability. All right, so these are the overview. We have basic probability concepts and definition, sample space, events, all right? Operation of events. This is something to do with, it's similar to set theory. Those operation with sets. All right? Union, intersection, then counting methods. How to do multiplication. We know how to do multiplication, but how to apply this principle in helping us to do counting, and also addition principle. Then permutation, combinations, and probability. Basically, there are 3 approaches to probabilities. What are these 3? The first one is the one that you're familiar with, based on counting, based on how many possible outcomes as the denominator, and what are the possible outcomes that favor to the event. So take the ratio, that is the definition of probability. The other one is to look at the relative frequencies. All right? So, for example, if I want to know what is the probability that an accident occur at the pedestrian crossings next to S17 bus stops. You take bus here, right? So what's the chance of having an accident there? So how do I define the number of possible outcomes? There are only 2 outcomes. Either there are accidents or there are no accidents. So what we do is to take certain period and look at how many cars passing through this, and then check how many accidents occurs. Maybe none. There is 0 probability, but it is not realistic. There will be chance, but the chance may be very small. So my point is, we have to look at the relative frequencies. But if I go back to a simple example, it's like that. Toss a die. What's the chance getting a 1? Everyone knows, right? I hope everyone knows, right? Supposed to 1/6, right? Am I right? Why 1/6? Toss the die, it shows the outcome. So the outcome can be 6 possible outcomes. 1, 2, 3, 4, 5, 6. 1 is the only one that favor to my statement. All right? So it's 1/6. All right? But alternatively, I don't know how to count. I don't understand all this. I just do the experiments. I toss the die, let's say 10 times, and see how many ones are there. All right? I can toss the die 100 times and see how many ones are there. Do you think these 2 numbers, the ratio, how many ones in 100 tosses and how many ones in 10 tosses are the same? It's likely that they are not the same. All right? But if I toss the die 1,000,000 times, then there will be roughly 1/6 of the times that you will get ones. All right? So the more times that you toss the die, the more accurate to 1/6. 1/6 is the answer based on the theory. All right? Relative frequency is through experiment. I got tossed 1 million times and see how many times that I got the ones. All right? So that's a relative frequency. We'll touch that a bit. All right? The third one, you don't have to worry at this moment. It's called Bayesian approach, but I will not discuss that. All right? And axiom of probabilities. I don't know whether in School of Computing you talk about axioms. In mathematics, we like to talk about axioms. You know what's axioms? It's the basic foundation thing. Everything builds on the axioms. That means you cannot challenge the axioms. These are the real stuff. All right? Every other properties about probability can be derived from these axioms. All right, so that's called axiom of probability. So we try to look at it and appreciate it, and then the other properties of probability will be derived from these axioms. Basic properties, conditional probability, this is really a tough one, and multiplicative rule of probability. So all this will be covered under the probability section. Oh, total probability Bayes theorem. All right. Independent events. This word is very important. It's like a magic word. So remember that. So must know what it means. All right, we'll cover that. Independent. All right, okay, let's start. Sample space and sample points. So the word sample is a little bit misleading. All right, but basically what it says is that let's consider, we define what is observation. It's very vague. What is observation? Observation basically is something that you get some information. It can be just numbers. So obviously numbers can be considered as observations. But also, not numbers. All right, any characteristics can be considered as an observation. Like for example, I consider your gender is not 0, 1, right? It's female or male in English, right? All right, so it's male or female. These are not numbers, but it's considered as observations. All right, so any numeric or categorical information is considered observations. And then we consider the way that we generate this information is considered as a statistical experiment. So basically, we do something and get some observation. All right. So then, now we can define what is sample space. Sample space is basically, you just remember, it is the set of all the observations, all the possible observations, Well, let's consider some examples. So toss a die. Oh, by the way, you may find it very simple, very boring to talk about toss a coin, toss a die. But let me warn you, or suggest to you, these are very simple examples that if you understand how it works or how it illustrates the principle or the properties of what we discussed, then you can extend it to other situations. So you better understand the case. All right. So start with toss a die. So this is my experiment. All right. What are the outcomes? So if I consider the outcome as the face up, then it will be just 1, 2, 3, 4, 5, 6. Consider it is an ordinary die, normal one. Have you seen some die with more than 6 faces? Right? We see here. So here, we restrict to 6 faces. The ordinary cube, all right, 6 faces. So 1, 2, 3, 4, 5, 6. Each face with a different number. You can have a die with all ones in all the 6 faces. Here we consider normal one with 6 faces with 6 different numbers. All right, so this is my sample space. All right. Now, but on the other hand, if I'm not interested in the number itself, I'm only interested in the outcome. only whether it's an odd number or an even number. So in that case, my sample space consists of only two outcomes. So that will be even and odd. So you can see, for the same experiments, depends on what outcomes that you're interested in. All right? Then you define your sample space. So I have a third one, which is not in the lecture notes. I toss a die. I see where it lands. And the outcome is the distance from where it lands to where I stand. Is that outcome of my experiment? Yes, right? Then in that case, what are the possible outcomes? It's continuous, but what is the set of these possible outcomes? Theoretically speaking, it can be from 0, it drops where I stand, all right? Or up to infinity. If I'm a Superman, I can toss the die and then it lands far, 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 far away in the next planet or next solar system. But usually it's not that. Maybe 50 meters or even 30 meters is long enough. So the sample space may be range from 0 continuously or in the interval between 0 up to 30 meters or maybe even less. So my point is, okay, look at the experiment. The experiment is to toss a die. I see where it lands. I can look at the surface, look at the face, the value on the face, or look at whether it's even or odd number, or look at where it lands. All right? So it depends on what you are interested in. Then define your sample space. All right? So here is toss two dice. So these are the possible outcomes. Now I have a questions. You understand this one? This means that there are 36 of them, 36 pairs. All right. Now I toss two dice. I throw two dice. How do I know it is 1, 2 or 2, 1? I can only see one die is 1, the other die is 2. So whether it's 1, 2 or 2, 1. Are they the same? It's a very tricky question. If you just look at the outcome, you can only see one or two dice, one with 1, the other with 2. All right? But in fact, the question may be clearer if I paint the die, first die with red color. I call it red die. And the second one, a blue die. Right? Then red is the first number indicates the outcome of the red die. The second indicate the second of the pair, the second value of the pair indicate the outcome of the blue die. Then 1, 2 means that the red die is 1, the blue die is 2. While 2, 1 means the red die is 2, while the blue one is 1. So they are different. Why we have to consider that? 1, 2 make it easier. So long as I see 1 and 2, then it's 1, 2. Why have to distinguish them? Okay. Before I answer these questions, let me ask you. In Singapore, for those who are from Singapore, you know what is 4D, right? It's a very popular game. All right, 4D. That means you try to bet on the outcome. There are 4 digits from 000 to 9999. All right? So I go and buy 4D, buy one number. Let's say 1, 2, 3, 4. Now, what's the chance that I win whatever prize? That means the number comes out as a winning number. What's the chance? How many possible outcomes? 10,000. Is it 10,000? 0000 to 9999, 10,000. And only one number that I only buy one number, 1, 2, 3, 4. So it's 1 out of 10,000. All right? But on the other hand, if I look at it, to me, there are only 2 outcomes. What are these 2 outcomes? Winning or losing. Right? Two outcomes. Now the problem lies in, is it equal chance of getting winning and losing? In this case, no. I buy 1, 2, 3, 4. Any other numbers come out, I mean, if the 1, 2, 3 does not come out, I lose my game. All right? So they're not equal. So when we consider all this outcome sample space, the key point is, the next step, in fact, is to make sure that all these outcomes are equally likely. So that's why I cannot consider 1, 2, 2, 1 as one outcome. I mean, I cannot say one, I see one die has 1, the other die has 2, consider as 1, 2. All right? I have to distinguish between the two dies. So the first one is a 1, the second one is 2, or the first one is a 2, second one is a 1, are different outcomes. By doing so, I make sure that every outcomes here are equally likely. All right? So that's why it's important to distinguish between them. All right? So here is another. This one, the experiment is like this. I toss a coin. Okay, if it's a head, then I continue to flip it. So the second outcome will be either a head or tail. But while if it's a tail, I don't flip the coin, but instead I do another experiment. I try to toss a die. So these are the possible outcomes. So the point is, in this order pair, the first outcome is tossing a coin. So there are two outcomes only, head or tail. While for each of them, all right, I will look for the outcome of the second experiment, the second part of the experiment. So it will be a toss a coin if the outcome is a head in the first coin. So you can see that it is head, head. Because the outcome is a head, so I have to do a tossing the coin. So the possible outcomes are head or tail. But while if it's a tail, then I have to toss a die. So the outcome will be 1, 2, 3, 4, 5, 6. So these 8 possible outcomes are these are the 6 possible outcomes of this experiment. All right? Are these equal likely? Are these equal likely? Someone say no. So are these equally likely? So that's what we're going to learn. Sample space means that the outcome of these experiments must be one of them. All right? So in other words, probability for each of these outcomes add up has to be 1. So you have to check that. All right? So you ask yourself, there are altogether 8 outcomes here. So if equally likely, then each one is 1x. So that's head probability is 1x. Makes sense to you or not? No, then that means they are not equally likely. All right? Okay. So the strict times index. All right? So that one, these are the possible outcomes. Right now it's about 3,000 plus. All right? The strict time index is up to 2 decimal places. So these are the possible sample space. All right? In fact, the numbers, all right, maybe from from 100, or can go down below 100, up to maybe 10,000 or even higher. But at this moment, it's about 3,000 plus. Okay, so here is another example, drawing a ball from a box with 3 balls. All right, so these are the outcomes. We are taking 2 balls, so we use the order pair to represent it. So the first one, okay, can be one of the 3 balls, black, white, or red. All right. So these are, but then after you take the ball out, then there are 2 balls left, so the other outcomes will be the remaining 2. So altogether, there are 6 possible outcomes. So again, you ask yourself, are they equally likely? All right? Are they equally likely? All right. Sample point is nothing but just the outcomes. Each element in the sample space, each outcome is considered as a sample point. So it's just a matter of definition. So we call that sample points, but in fact it just means that it's the outcome in the sample space, or in the all possible outcomes. All right. So in this case, sample point is one of these 6 numbers, and in this case it's either even or odd, and in this case it's one of the 6 numbers. One of the 36 numbers. And in this case, one of these 8 numbers, 8 possible outcomes. And in this case, it can be any one of these numbers, or 3,000 something, or 2,000 something. And in this case, any one of these are considered a sample point. All right. Yeah. Maybe it's time to. This is a point where we can. Do you need a break? I don't need a break, but do you need a break? Huh? Cannot make the decision. Then I make it for you. Do you need a break? No need. Huh? Okay, so I asked opinion, all right? Let him represent the whole class, so I continue to talk. Because you don't voice out, huh? Okay, let's continue. Events. Now, you will see this term appear frequently, events. Event basically is a subset or a collection of sample points, or a part of the all possible outcomes. All right? So a subset of the sample space. To translate means that it's a subset of all possible outcomes. If, for example, odd numbers in this toss a die, so it means that it is equivalent to a set consists of 1, 3, 5. 7 is an odd number. Why it's not there? 7. How come it's not there? Because it's not part of the all possible outcomes in this experiment. All right? So only within 1, 2, 3, 4, 5, 6, pick the odd numbers. All right? If it's even numbers greater than 4, then it is 5 and 6. And even odd, then odd numbers occur, then it falls into odd. All right? Oh. So in this second example, rolling a pair of dice, the sum of the dice equal to 7. So these are the possible outcomes that give you the sum equal to 7. All right? Altogether 6 of them. All right? If I change the sum of the dice, of the 2 dice, equal to 8, how many are there? Okay, you can use brute force to count, but I want you to think of it like this. I have 2 dice, right? So I can write down the first outcome, 1. All right? So, or in general, if the first die is an I, if I want the sum equal to 8, then the second die must have 8 minus I, so that the sum is equal to 8. I plus 8 minus I equal to 8. All right? Okay. My point is you have to think it in a more general setting. So once I identify this relationship, then I start with 1. Is it possible to have I equal 1? And the answer is no. So I cannot start with I equal 1. So I start with I equal to 2. All right? So 2, 6. And then 3, 5. Can I have 6 for I? Yes, then I have 2. So how many sample points are there? 5 of them. All right? So I want you to understand that, yes, sometimes brute force, all right, works. But it's even better if you think of to put it in a more general way. So if I want the sum to be 8, then the number, the first one is I, then the second one, because of the sum equal to 8, must be 8 minus I.
8 minus I. All right? So now I start with I equal 1. Sorry. 8 minus 1 is equal to 7, which is not one of the outcomes of one of the values. So we get rid of that. So start with I equal to 2. Up to 6. All right? I equals 6. All right. Okay. The third example is this example about tossing a coin and then followed by tossing a coin or die. And so event is no die is thrown. All right. So, sorry about it. No die, that means it's only these two. Only these two. Because these two, all right, will give you an outcome that no die is tossed. So a white ball is chosen. So these are the white ball. It doesn't matter whether it's the first one or the second one. Again, I have 3 balls in the box. I take 2 balls, right? So I can just grab the 2 balls without considering the sequence. I just take 2 balls out of the box, all right? So then I look at the color. 1 white, 1 black. 1 white, 1 black, all right? So which one is it? All right? So, okay. What I'm trying to emphasize is that I want to make it equally likely. So that's why I consider, instead of grab the 2 balls simultaneously together, I take it one by one. I take 1 ball out, look at the color first, and then take the second ball out. By doing so, I'm sure that the outcomes are all equally likely. But if you grab 2 balls, it makes it more complicated. All right? Because if you take 2 balls, you look at 2 balls, if you want to answer the question, what's the chance that you got 1 white ball? All right, so it's difficult to address that question. But if you treat it as equally likely outcomes, then you just count how many outcomes that give you 1 white, including, So all these are 1 white ball. All right, so here are more examples. You can look at it. All right. Now, we look at something called simple and compound events. Simple simply means that it consists of only one outcome. We call it simple. One outcome of what you are interested in. Compound event is one with more than 1 outcomes. All right? So just remember, simple means that only one outcome, while compound means more than 1 outcome. So in this case, an odd number means that it's a compound event because it consists of 3 outcomes. All right? While a number greater than 4 is also a compound event. That means it has more than 1 outcome. A simple event is just got a 6 in this experiment. So that is a simple outcome. All right. So for the second one, there are only 2 outcomes, even or odd. So if you are interested in odd, there's a simple event. If you are interested in even, it's also a simple event. All right? I have to stress. So if I throw the die and got a number 2, so what's the outcome? For B, what's the outcome? I got a 2. So what event is that? I'm interested only odd or even. Now I got a 2, so it's an even. All right? So it belongs to even. All right? Then I got a 4, it's also even. Got a 6, it's also considered as even. So what's the chance of getting an even, an event even? So it's equivalent to either you got a 2 or 4 or 6. Okay, so 3 possible outcomes. Because it's a, okay. So this one, the the probability of getting an even number is 1/2. All right? By looking at the sample space and the sample point. There are only two outcomes in this sample space. Even is one of them. So that's how I look at it. And even and odd are equally likely in this experiment. All right? So it's 1/2. Another way to look at it is, how do I get even number? 2, 4, 6, I got even. All right? 2, 4, 6 are 3 outcomes out of 1, 2, 3, 4, 5, 6. So it's 3 over 6. Again, it's 1/2. So my point is, there are 2 ways to look at this question. What is the chance of getting an even number? Odd numbers. What's the chance of getting odd numbers? So, if you treat it as 2 outcomes, odd and even, you ask yourself, are they equally likely? If the answer is yes, then getting an odd number is 1/2. All right? In this example, are they equally likely for getting an odd and even? Yes, 1, 2, 3, 1, 3, 5 on one hand and 2, 4, 6 on the other hand. All right, so that's one way to look at it. The second way to look at it is that, okay, when I say even number is corresponding to 2, 4, 6, these 3 outcomes. All right, and it's 3 out of the 6 possible outcomes. So it's 3 over 6. All right, so they're the same. All right, so what I mean is that if I look at it as, okay, the event, okay, if I look at this as S and A as 1, 3, 5. So the probability of getting an A is 3 over 6. While this one, probability of getting an odd number is 1/2. Consider that they are equally likely. All right? So, so always ask yourself, the outcomes that you're considering, are they equally likely? All right. Okay, so getting a sum of 2 dice equal to 7, so it's considered as compound event. Simple event is that the sum of the dice equal to 2. There are only one sample point, one outcome that related to the sum equal to 2. That is, the first die is a 1, the second die is also a 1. But if I want the sum to be 3, there is no more simple event, because it consists of the first die. If I want the sum to be 3, the sum equal to 3, then it can be 1, 2 or 2, 1. So in that case, it is not a simple event. Right. Why we talk about so much about simple and because simple event, okay, compound events make use of all this. I mean, combine all these simple events. So the combination sometimes is okay. If they are mutually exclusive, then you just sum them up. Oh, okay. So here is other examples. If the sample space is the whole real line, positive real line, all right, like the life in years, then what's the chance that the lifetime is less than 5 years? So this is an event. So we have something, and the lifetime can be from 0 onwards. All right. But we asked, what if we restrict to the lifetime to be less than 5? So this is the event. The event that the components survive 5 years. So less than 5 years. All right. So the lifetime is less than 5. All right. And these are the two very, these two terms must we know. We must know. One is sure event. Sure event means it must occur. That means it covers all the possible outcomes. The other one is no way that it can occur. It's called null event. Null event. So, null event corresponding to there's no way that this outcome will come out. Sure event is that this event will come out. If I say toss a coin, it can be I mean, what's the chance that it's got if the event that I'm considering is 1 and 2, then there's not sure event. But if I say that I want the outcome to be 1, 2, 3, 4, 5, 6, that is sure will happen. All right? So these are the two terms, two special events, sure event and null event. Sure event is considered as the sample space, and the null event is considered as an empty set. This notation, all right, is empty set. That means the set consists of nothing. Operation of events. This is important because when we want to compute the probability, we have to know how the events can be simplified or can be worked with. All right? So, first of all is the union and intersection of events. So suppose we have two events, A and B. All right? So, now this event basically consists of the elements of the sample space or the outcomes. A is a set of outcomes, B is another set of outcomes. Are A and B different? Are A and B different? I did not say anything, right? They can be different. Can they be the same? Yes, they can be the same. All right? So, union of two events. This is the definition. All right? By the way, I think a Venn diagram, a picture will help a lot, but you cannot use it as a proof, but you can use it to give you some insight of how to do the operations. So, A union B, A union B, A union B. So this is A union B. That means any elements that you can find either in A or B or in both, then it's considered as the set A union B. All right? And intersection of two events, then it is N. So the elements or the outcomes must in A as well as in B. So if you draw the, no picture. First of all, I write down sample space, all possible outcomes. A, those outcomes belong to event A. B, those belongs to B. And those belong to A at the same time belong to B is this part. All right, so we have to look at this part. This is the A intercept B. And others, complement, this is again very useful. Complement events. So if this is A, then the rest is called A complement. So those outcomes that belong to the sample space but belong to the, it's not in A, so it's the rest. All right? So let's look at an example to illustrate all this. So we consider tossing a die, 1, 2, 3, 4, 5, 6. So A is 1, 2, 3, B is 1, 3, 5, and C is 2, 4, 6. So I give you explicitly what are these events. Can you describe what is A? What is event A? Yeah, so it is A is an event that you got a number less or equal to 4. Less than 4. Less than 4. Or less or equal to 3. B is an event that you got odd numbers. C is an event that you got even numbers. How about this event? If I have a D, let me know if you can describe this event in a simple terms. All right. So my point is that sometimes an event can be described by words, but sometimes it may not. You may not able to describe it easily. All right. So what 1, 2, 5. Then Okay, so A union B. So those outcomes that belong to A or belong to B. So what you look at is, okay, A must be there. B must, 2 must be there, 3 must be there because it belongs to A. All this belongs to A. Then you go to the next one because we are talking about A union B. So B, we have 1. 1 already there. So 1, 3. But 5 is not there, so I have to add 5. So the union will be 1, 2, 3, 5. 1, 2, 3, 5. All right? So now I find a way to describe 1, 2, 3, 5. So it is an event. It is an event that consists of a number which is either an odd number or a number less or equal to 3. Basically, I combine the two description. All right. A number less or equal to 3, as well, or an odd number. All right. How about A union C? So it's 1, 2, 3, 4, 6. All right. And B union C is odd and even number together, so it covers every outcome, so it's equal to the sample space. Then, immediately we know that what is C complement? C complement will be the same as B. What is C complement? C complement are those outcomes that do not belong to C. All right? So do not belong to C. So it is equal to 1, 3, 5, which is B. All right? Then A union B union C. Now, by the way, this is also important. A union B union C. So we have two operations. You can either do it A union B first, and then union C. Just like 1 plus 2 plus 3. You can either add 1 plus 2 first, so it's 3 plus 3, so it's equal to 6. That's one way to do it. Or alternatively, I can do 1 plus 2, 3 first, so it's equal to 1 plus 5 equal to 6. That means I do this first, all right? So in addition, it doesn't matter which one you do first. So for union, whether you A union B first, and then the results you union C, is the same answer. So the answer is S. Okay, so it doesn't matter. But if, on the other hand, okay, this A intercept B, but this may not be the same, so you have to be aware of that. This may not, I put a question mark. Oh. So this may or may not be the same. You have to check, all right? So in fact, this in general is not true. We can see it here. Okay, A intercept C is 2, and B intercept is empty set. So this is talking about intersection. So intercept, A intercept B intercept C. It doesn't matter which one you intercept first. So, if I do A intercept B intercept C first, so it's A intercept B intercept C, no common element, empty set. Do you find any common elements in these two sets? No, so it's empty set. So the answer will be the same. All right. So in other words, so long as you intersect many events, it doesn't matter how you intersect. Which the order is not important. But if like in the last statement here, so there's intersection and union, then you have to be careful. So you can see that if you do the first operation first, intersection means, all right? And if you do the union first in the second statement, then the answer are not the same. So in other words, the order will be important if the union and intersections are included as part of the equation or part of the operations. All right? If all the operations are unions, then it doesn't matter. If all the operations are intersections, it's not important the order. All right. But while if there's some union, some intersection, then you will be careful. The order may be different. So, in other words, so what happens if I see something like this? So what I'm going to do? You know that the order is important. So if no indications, all right, so we work from the left to the, is it? Yeah, from the left to the right. Follow the order. But to ensure that there's, no ambiguity, you better put a bracket there, all right, to identify which one you want to do first, all right? Okay, so make sure that you remember this important fact. If the operations are mixed, then the order is important. If the orders are only one type of operation, then it doesn't matter. All right, so here is the complement. Now, this is very interesting. All right, you notice that the intersection of two complements, A complement intersect B complement, in this example is 4, 6, while the complement of two unions is also 4, 6. So, this is example. So the question is, are these always true? Are this, okay, what I mean is, this one, is it true? Always. It doesn't matter what the two events are. All right? We can prove that, yes, this is true. But you can also help you to understand it. Think of it. What if this is A, this is B? What is A complement? A complement will be this part plus this part. All right? This is A and this is B. So A complement is what? And then B complement. So after you got, okay, let me see whether I can have different colors. Color. Okay, B complement. B complement. Excluding the B. Then intersection of these two. So only see those with red color or blue color. So it turns out will be something like this. I don't know, you can try it yourself, but basically you only see this part. These are the intersection. The A union B complement. So the two are the same. The two are the same. This is very important because sometimes it's very difficult to look at A complement and B complement and then followed by the intersection. But on the other hand, it may be easier to look at A union B and then take the complement. Or maybe the other way around. So this relationship between the two are very important. Very useful. What I mean is very useful. So think of it. The complement, the intersection of two complements events is the same as the complement of the two unions. The unions of two events. All right? Again, this is an important concept. Exclusive, mutually exclusive events. All right? Yeah, I'll ask them to open the door. Okay, So what is mutually exclusive event? By the way, when you do all these computations, make sure that you understand the definitions. Things are not based on your intuition, based on the definition. When we say two events are mutually exclusive, it means that there are no common outcome between these two events. That means the intersection are empty set. A in union B is equal to empty set. So then we call them mutually exclusive. All right? Mutually exclusive. It still can be represented in the Venn diagram. So it's very simple. Two events are mutually exclusive if there are no common outcomes. No common outcomes. Then we say that they are mutually exclusive events. It makes life much easier. Because, think of it, if I asked, what is the chance of A union B? Now, if A, B are mutually exclusive, then this is equal to A probabilities plus B probability. If A, B are mutually exclusive. All right? So it makes the computation much easier if they are mutually exclusive events. All right? So these are mutually exclusive events. So these are some examples. B and C are mutually exclusive. All right. A and B is not because A intercept B. 1 and 3 are the common elements of A and B. So A and B are not mutually exclusive. So 1 and 6 are mutually exclusive. And A and A complement are mutually exclusive. All right? Union of n events. So you have n events, the union of it represented by this. All right, A1 union A2 union A3 up to U. Okay, so in other words, this union will have all the outcomes that either belong to one or more than one of these events. Okay, I believe some of you hate this kind of thing, but this is how a mathematician do things. So first law, we start with A union B. If we have 3 events, then A union B union C. We have 26 events, okay, fine, up to Z. But if I have 27 events, then what? All right? So we start with A1. Use number to identify it. So the second is A2. Up to AN. N can be any numbers. So we are talking about the union of n events. All right? Now, so this is what we mean by n union of n events. So by definition, it means that it is a set consists of all the outcomes, and each outcomes either belong to A1 or belong to A2 or belong to A3 or belong to AN. It can belong to more than one of the events. All right? So this is the notation that we use. Union AI. You have to learn how to read this one. It means that we are doing the union. Union of what? Union of the events A1 up to AN. So the general form is AI. And I is from 1 to n. So if union AI, I equal 1 to 3, then it means A1 union A2 union A3. That's what it means. All right? So similarly, what does that mean? It means that we are doing intersection, and it's A1, A2, A3, A4, and intercept of all this. Which means that this set or this event consists of all the outcomes that must belong to A1, A2, A3, and A4 all together. This one does not belong to this set. All right? So that's the intersection of n events. So naturally we ask, So these are the basic properties about the events. So you must be aware of that. A intercept A complement equal to empty set. All right, that's the definition from the complement of events. A intercept empty set is empty set. A union A complement is S. Complement of a complement equal to itself. So you can think of it A complement. So the complement of A complement will be A again. All right? So we have discussed this part. Complement of A intercept B equal union of two complements. All right? Okay. So the opposite is also true. The complement of two unions is equal to the intersection of A complement intercept B complement. Now, if you want to appreciate these properties, you go and take the examples that we used for for the throwing a die. S is 1, 2, 3, 4, 5, 6. A is 1, 3, 5. 1, 2, 3. B is 1, 3, 5. And C is 2, 4, 6. And use it to apply. See what happens. You try to evaluate. All right. All the property, all the events, and then you appreciate how this properties. All right. So this is the union of A intercept. So this we have two operations here. You can think of it. It is like for example, A times B plus C. So it's equal to A times B plus times A times C. So A union B intercept C. So it's equal to A union B, A union B, A union B, intercept A union C. It's just like A times B plus A times C. All right? We can prove that. And same here. So A intercept B union C is the same as A intercept B first, and then A intercept C. And look at the union of the two. All right? So I don't confuse. I'm not saying that union is equal to multiply, intercept is equal to plus. I did not say that. So it's similar properties. A union bracket B intercept C is equal to, first of all, union first, and then take the intersection of the two unions. Okay. Now this is very interesting. A union B. So this whole thing is A union B, but it is equal to A union A complement intercept B. Now A complement intercept B is this part. A complement is supposed to have this part, but we exclude that. So A complement union B is this part. This is the, let me change the color. So this part is A complement intercept, sorry, my mistake. Intercept B. Intercept B. So it just breaks down A union B into two parts. One is A, the other one is A intercept with B complement. The same thing here. How about if I look at A? What is this part? A intercept B. And what is this part? The two expressions, the two events, the two sets on the right hand side, are they mutually exclusive? Are they mutually exclusive? Think of it. One is A common to B. The other is A common to B complement. Is there anything common to B and B complement? No. There are no overlapping between the two. So therefore, these two events are mutually exclusive. So therefore, I can put them together. So in other words, I partition the A into two parts. One is common to B. The other part is common to B complement. So that's how I got the A. So that's one way to look at it. All right? So if you manipulate all this skillfully, you will find ways to solve your problems. So instead of looking at A alone, I separate to look at A intercept B and A intercept B complement. This is what we have. All right? Okay. We discussed this one for two event case. But the name is not important enough. It's called De Morgan's law, but basically we have this property before, right? A intercept B equal to A complement union B complement, right? But now extend to n events, then A1 intercept up to AN, all right, complement is equal to A1 complement union A2 complement and so on. All right? So this is the two, basically extend the two events case. All right? So remember, union, all the events, take the complement, is equal to the intersection of all the complement events. Similarly, the complement of all the intersections together is equal to the union of the complements. We are not going to prove that. It's just a result that you may use it. And in order to appreciate it, you just remember the two event case. You maybe extend it to three event cases. Then you will appreciate this De Morgan's law. So here are some examples. I think you can read the examples yourself. All right? Yeah. So, yeah, I think I stop here since we don't have a break, right? Yeah. Yeah. And I'm the one talking, not you. You're just listening, right? Okay, I think I stop here. Then hope I will see you tomorrow. Yeah. Hope.